All right. Well, when we last spoke, I had started off with a application of the law of Biot-Savart, and I've got a couple more of those that I need to work, and then we'll go into Ampere's law, and that should finish up chapter 28 for us. So I just want to start off by sharing my screen and right now Ampere, or excuse me, right now Biot-Savart law, and then we'll start working an example. So let me start off by sharing my screen. That should pop up any minute. So the law of Biot-Savart basically says that the differential magnetic field is given by mu zero I over 4 pi times. Now here's the weird part. It's dl cross rp minus rdl divided by the magnitude of rp minus rdl, and that is raised to the third power because I've got a RP minus RDL in the numerator, and that makes it basically makes the number of magnitudes of distances in the denominator be equivalent to 2. So it's a 1 over r squared law, just like Gauss's law, and just, well, like Gauss's law results in, but like Coulomb's law, where you had K Q1, Q2 over R squared. This is essentially the equivalent of R squared. The vector dl is a differential line element that points in the same direction as the conventional current, and the RP is a vector that points from the origin of your coordinate system to the point P at which you wish to calculate the magnetic field, and RDL is the vector that points from the origin to the differential line element DL that points in the direction of the current. So that's the way we use this. What I was going to do is we already worked it out for a infinitely long straight wire, and we worked out that the magnetic field due to an infinitely long straight wire carrying a current I is B vector is equal to mu 0 I over 2 pi r times, excuse me, times the theta hat vector. And that's assuming that the electric field, or excuse me, that the current in the wire is going in the positive z direction, and the wire itself is right along the z-axis. And then if you have the z-axis is where the current's going, then automatically the theta hat direction is the direction of the magnetic field around it. So we had already used that expression, and the result was, as I just said it, I'm going to write it now so that you'll have it in picture form as well as word form, because I know how hard that is. So if you're trying to find the strength of the magnetic field a distance r away from the current carrying wire, yeah, excuse me, from the current carrying wire, then the strength will be mu 0 I divided by 2 pi r, where r is that perpendicular distance from the wire to the point at which you wish to know the electric or the magnetic field, and it points in the theta hat direction. And last time I spent a little bit of time showing you what the theta hat direction meant. Remember, if you're talking about a point on the x-axis, then the theta hat direction is basically the same as the positive y direction. If the point at which you wish to know the magnetic field is on the y-axis, then the theta hat points in the negative I hat direction. And if the point you wish to calculate the magnetic field is on the negative x-axis, then theta hat is the equivalent of the positive j hat direction, or the positive y direction. And if it happens to lie on the positive x-axis, then the theta hat is equivalent to j hat, or the positive y direction. So that's just a rough idea of how it sort of goes around the coordinate system. So I wanted to make sure y'all could visualize that, because we're going to use the symbol just to make it more clear exactly what the direction of this magnetic field is. Now, the example I'm going to work now, I'm going to start off by drawing a coordinate system. And this is very much like an example that's in the book, but it's I've oriented the coordinate systems a little differently, and that way I'm not actually calling it an example from the book. It's just a derivation or example by me. So I'll just call it example. But what we're going to have is a x-axis that points out of the page, a y-axis that is in the page and points to the right, and a z-axis that's in the page and points up. Uh, Now, the actual current carrying wire that we're doing a calculation for is going to be a circular loop. So I'm going to attempt to draw that as nicely as I can. So roughly like this, and then roughly like this, and then this part goes like that, and then this part goes like that. That turned out horribly. So I'm glad that y'all all came and saw this horrible circle I did. But anyways, that's what it turned out to be. Whew. Okay, so that's supposed to be a circle lying in the. Oh, I don't even know what happened there. That's supposed to be a circle lying in the XY plane, and the current is going to go in the theta hat direction. So what we're going to do now is I'm going to try to draw another, oops, evidently I'm going to erase a bunch of stuff because this stupid program switched to eraser all the time. Makes me very angry. So that's my attempt to make it a wire, so that really made it look a lot worse. Ugh. And the third time is not a charm, but close enough. All right, so what I'm going to do is imagine a distance r because this loop of wire has a radius big R, and I'm going to imagine that I sweep that little radial line out by an angle theta, and that makes this little mark right here, and then I allow that angle theta to change by an amount d theta, and that's what this angle is. So this angle in here is d theta, and now that allows me to define the differential line element dl as dl is equal to, and remember S equals R times theta is the expression for the arc length when an angle is stretched. Excuse me. When a radial line is passed from an angle of theta to theta plus d theta, the dl becomes r d theta, and of course it points in the theta hat direction. So that's our differential line element. Now, according to the law of Biot-Savart, we not only need a dl vector, we also need an rp vector and an rdl vector. And what we're trying to calculate is the the magnetic field, a distance z up above the xy plane. So what I'm saying is this point right here is the point P at which we wish to know the magnetic field. So that vector RP is the vector that points from the origin to that point. And the vector RDL is a vector that points from the origin to the tail end of DL. So that little green vector right there, that green vector is RDL, and this red vector is RP. So, can anybody tell me what the form of the vector RP is? In other words, can you give me components times I hat plus a component times J hat plus a component times K hat if you need all three of those for RP? And additionally, can you do the same thing for RDL? And we've already worked out DL. So can someone tell me what RP is going to be? Anyone? I'm not getting any takers. So the big thing to notice with vectors, one way that you can always calculate a vector is you can take a point in space that you wish to be where the head of the vector is, and then you can take a point in space where you wish the tail of the vector to be, and you can take the x coordinate of the head minus the x coordinate of the tail, and that will make the x component of the vector. If you do the same thing for the y coordinate of the head minus the y coordinate of the tail, that'll give you the y component of the vector. And if you do the same thing for the z component of the head minus the z component of the tail, that'll give you the z component. So that's a trick that always works no matter what, as long as you're talking about finding vectors in a coordinate system and you know the endpoints. So, like Alex says, he's saying RP is something K hat, and that's exactly right. And since we're along the z axis, I'm going to use the variable z as the magnitude. So RP is in fact going to be z K hat. That's all you got to do. You're looking for it to find the magnetic field at distance z above the xy plane. So we're just going to call the magnitude of that vector z. How about this one's a little trickier. Can someone tell me what the x component of RDL is? And I don't actually have to put a vector symbol over the DL down there. I just did it out of habit. But don't waste your time trying to write that. So the vector RDL, you see it down there in green. Anybody guess what the x component would be? Let me draw a line to see if that helps you any. So this line right here represents a vector that is equivalent to the x component. And of course, the other green line that seems to be perpendicular to it and therefore is parallel to the y-axis, that one would be the y component. So now maybe y'all can tell me what the x component of RDL is? Anyone? Yes. The x component will be cosine theta. The only thing you're missing is the vector, is the magnitude capital R, because that's how long it's got to be R times cosine theta to get that x component. So RDL is going to be R cosine theta I hat, which is essentially what you had said. And then the y component is going to be R sine theta, and that's the times j hat. So we now have all the vectors that we need, and that's the biggest part. If you can now put them all in that integral formula, then you have basically what's required to get you the lion's share of the credit for the problem. Now we also have to compute RP minus RDL, so I'm just going to do that. But remember, it's nothing magical, so it's just literally subtracting one vector from the other. So RP minus RDL is going to be z k hat minus r cosine theta I hat minus r sine theta j hat. And then, of course, that means we also need the magnitude. The magnitude of the RP minus RDL vector is, and if you want to see how this works, the actual RP minus RDL vector is actually the vector that points from here to here. So this vector is RP minus RDL. And that might, by realizing what that is, that might be able to help you more easily figure out what the actual magnitude of RP minus RDL is. So anybody want to take a guess at what the magnitude of RP minus RDL is? I'll give you a hint. It starts with square root. The big thing to notice on this vector is that it's got two legs, if you will, if you're thinking of Pythagorean theorem where you have two legs and then a hypotenuse. This has two legs that are perpendicular to each other. One is the green vector, and you know the magnitude of the green vector is in fact just r, even though it's r cosine theta I hat plus r sine theta j hat. If you actually tried to do the Pythagorean theorem on that, the sine squared plus cosine squared would give you 1, so you just get plain r. The other vector, the other leg, is the red vector, and that has a magnitude of z. So I'm going to call this r squared plus z squared is the magnitude. And that's it. If you wanted to take the time, you can actually use the three-dimensional Pythagorean theorem for rp minus rdl. It would be z squared plus r squared cosine squared theta plus r squared sine squared theta, all of that under the square root. But again, the two last terms have r squared in it, so you could factor out the r squared from those last two terms, and that would give you z squared plus r squared, parenthesis, cosine squared plus sine squared, close parenthesis, cosine squared plus sine squared is 1, so that's why you get r squared plus z squared. Exactly, Alex. All right. So now we've got all the parts filled out. Now, if I just put it inside of the vector formula, then we'll have the actual lion's share of the credit. So B is equal to the integral of dB, which equals mu 0 I over 4 pi times the integral of, now we write dl, which is r d theta theta hat, and I'm crossing that with rp minus rdl, which of course is z k hat minus r cosine theta I hat minus r sine theta j hat. And all of that, of course, has to be over r squared plus z squared, and that's the square root raised to the third power, so that means it's to the 3/2 power. So that's what our magnetic field has to be. And like I said, if you got this part written down and I can look at it in your work that you turn in, then if it was a 15-point question, I'm probably going to give you at least 13 of those points. If it's a 10 point, I'm probably going to give you 9. But if it's bigger than 10, it's probably going to be maybe just 1 or 2 points less. So that would be more than enough, because the rest at this point is just doing mathematics. So if you could write that out like that, you're going to get the lion's share of the credit. So I'm going to go ahead and write up here and say B is equal to. Now, the big thing to understand with the theta hat is, last time I took the time to derive what theta hat is. This time I'm going to actually just use that result and compute the cross product accordingly. So mu 0 over 4 pi times the integral of r d theta. And then theta hat actually has negative sine theta I hat plus cosine theta j hat is really what that theta hat is. And then that's going to be z k hat minus r cosine theta I hat minus r sine theta j hat, like that. And then, of course, all of that is over r squared plus z squared to the 3/2 power. So in order to compute this cross product, I'm going to do this down at the bottom, and I'm going to do it in red just to make it stand out so it doesn't look like part of the integration that I was doing before. So I have negative sine theta I hat plus cosine theta j hat. That's going to be crossed with zk hat minus r cosine theta I hat minus r sine theta j hat. And we do a FOIL method here basically. So the first term, I'm going to get a negative sine theta from the coefficient of I, and I'm going to get a z because of the coefficient of the k hat. And I'm pulling those out in front because we know the cross product's a linear operation, so I can pull all the scalar parts out in front and then just let the vectors act on the vectors. So I have the negative sine theta times z times I hat cross k hat. Notice I didn't change the order. That's critical. This isn't regular scalar multiplication. When you multiply two things by a cross product, the order matters. So now I've got to take I hat and let it hit the second term. So negative sine theta I hat crossed with negative r cosine theta I hat. But I hat cross I hat is going to give me 0, so I'm going to leave that off. So I'm going to say plus 0. And then if I do I hat, uh, the sine theta crossing with the negative r sine theta j hat, that one's the difference. So you don't have an I hat cross I hat, which are parallel to each other. When you have them parallel to each other, the cross product's going to be 0. But if they're not, then it's non-zero. So in this case, I've got a negative sine theta, and I also have a negative r sine theta. So I'm going to make that a positive and make that sine squared theta and an r. And then I have I hat cross j hat. So that's what happens when the negative sine theta I hat hits each of the three terms. Now I've got to let the cosine theta hit each of the three terms. So I'm just going to write it way over here, even though the equals is over there, but I'm just trying to save some room. So this time I'm going to write plus z cosine theta. Now I'm using the cosine theta j hat, and that has to hit the k hat term, so that's why the z's out in front. But this time I get j hat cross k hat. And now I do cosine theta has to hit the second term, and in this case, we have plus, we have the cosine theta and another cosine theta, so that's going to be a cosine squared theta, and one of them's negative, so I have to put the negative out in front, and I have to put this in parentheses so the r can be there, but that's mainly because if I leave the r there, you might think it's cosine squared of theta times r, when it's actually cosine squared of theta parentheses times r. Now, when I did this one, this was actually j hat cross I hat. So I'm now going to write j hat cross I hat, and I'll show you how to work out that in a little bit. And now the last term I have to do is cosine theta j hat crossed with negative r sine theta j hat, but those two are parallel, so that's going to be a 0 as well. Uh, Now I can simplify this a little bit. I'm going to have negative z sine theta, and I hat cross k hat is actually I hat cross k hat. You can use the right hand rule, and the I hat is in the x direction, so that's out of the board. The k hat is up, so that's like that, and then my thumb is pointing to the left, which is the negative j hat direction. So I'm going to write negative j hat right there, and of course that negative is going to combine with the negative out in front to give it a positive, but the main thing is I got that part worked out. So let me put a little check over there showing that I've done that one. Now I've got 0, so I'm not going to worry about that. But then I have a r sine squared theta times I hat cross j hat. I hat cross j hat would be out of the board, and then j hat would be this way, and then that gives us the k hat direction. So in this case, it's going to be plus, oops, I want to switch back to red now. It's going to be plus r sine squared theta k hat. So that takes care of this term as well. Now I'm also going to take the z cosine theta j hat cross k hat. Well, j hat cross k hat is j hat, which is sticking to the right, and then cross k hat, which is up. So I see that now my right thumb is pointing out of the page, which is the I hat direction. So in this case, I get z cosine theta I hat. So plus, oops, wrong color again, plus z cosine theta, and this should be I hat, which I've been putting in parentheses just to make sure it's obvious that the I hat's not having the cosine of it taken. So now I've completed this term, and now I've got a negative r cosine squared theta j hat cross I hat. J hat cross I hat is j hat is the y one, so that's pointing to the right. I'm crossing that with I hat, which means sticking out of the board, and that's giving me a negative K hat because my right thumb is pointing down. So in this case, I'm going to say plus, or yeah, because it's going to be minus R. There I go, my wrong color again. Minus R cosine squared theta times negative K hat, like that. So now I've gotten the complete cross product computed. I'll put a check over that one too, and now we see that we've included everything. Now I can go back to writing the integral. So B is equal to mu 0 I over 4 pi times the integral. Now remember, I already had the r d theta in front of all this, so I'm just going to put the r d theta there. And then the rest was z theta hat cross that vector. So now I put in after this the vector that I just computed, which the negative z sine theta times negative j hat gives me z sine theta j hat. That takes care of that term. And then I have plus r sine squared theta k hat, that takes care of that term, plus z cosine theta I hat, that takes care of the third term, and then the minus times the minus gives me a positive r cosine squared theta k hat. Now I've completed the entire cross product and written it down, and I have r squared plus z squared raised to the 3/2 power in the denominator. So now I've gotten basically everything. And what we got to realize here is our integration variable is theta. And theta, in order to cover this entire circle, theta is going to have to go from 0 to 2 pi. So that's our integration limits is from 0 to 2 pi, or our range of integration is going to be from theta equals 0 to 2 pi. Now, you can probably tell that when I do something like calculating the integral of sine theta from 0 to 2 pi, or the integral of cosine theta from 0 to 2 pi, both of those are going to come out to be 0. So that's something that's helpful to know. And we'll work that out now. But that's also something that you can see from the symmetry of it. Just from the symmetry of it, if you look at the point that I have right now, according to where my dl vector is, that's going to have a x component that's in the negative direction. It's going to have a y component that's in the negative direction as well. But if you imagine the d theta that are the DL that we'd have exactly 180 degrees away, then you'd see that one would have exactly the same X component but positive and exactly the same Y component but positive, and therefore they would cancel them out. So you can see that generally speaking, the X components and the Y components should have become 0 just from the symmetry of the problem. So that's the kind of stuff that you want to catch so you don't have to do the integration, but I've explained it now mathematically as well as physically. So now I can go ahead and say mu 0 I over 4 pi. I'm going to pull out the r in front, and the r squared plus z squared to the 3 halves isn't going to matter at all either. So I'm going to put that as r over r squared plus z squared to the 3 halves power. And the reason we can do that is because our integration is in actual theta. So now I'm going to put square bracket around it, and I'm going to have the r that I already pulled up. The z is going to be right here, and I'm going to say z sine theta. The j hat, because it's one of the Cartesian unit vectors, those guys can be passed right through integrals and derivatives because they're not functions of position or anything, so you never have to integrate or differentiate them. But I'm going to take the integral of d theta from 0 to 2 pi of sine theta. That's going to be in the z hat direction. So, or excuse me, in the j hat direction. But you can see that the integral of sine theta is 0. So that got rid of that one. The next one, if you'll notice, I have two k hat components. The k hat r is r sine squared theta and r cosine squared theta. So this is going to be sine squared theta plus cosine squared theta, and then all of that is in the k hat direction, like that, and that's going to be an integral from theta equals 0 to 2 pi as well. But sine squared plus cosine squared is just equal to 1, so I don't have to mess with that at all. I'm just going to be integrating d theta, oops, which I left off. Oops, still leaving off. So there's the d theta, and then the k hat is right there. That has taken care of. I'm going to mark this off in green. I did this one first, and now I've done this one and this one. And all I have left now is plus. This is one where I could pull the Z out in front and I could pull the hat out in front. I didn't pull the Z out last time. I should have, but I didn't. But I did pull the J hat out in that first integral. So this is what's going to happen. I'm going to integrate from theta equals 0 to 2 pi again, but this time I'm integrating cosine theta d theta. And remember, that's from 0 to 2 pi, and clearly that's going to be 0 because remember the integral of cosine from 0 to 2 pi, it has that first quarter that's a positive area, and then it's got a quarter and then another quarter that are both negative, and then it's got another quarter that's positive. The quarter that's positive on the end and the quarter that's positive on the beginning add up to give you a positive half, and the two quarters that are upside down on the bottom, they add to give you a negative half, so you end up getting 0. So that's why that integrated the way it did, and we're ultimately left with just mu 0 I r over 4 pi r squared plus z squared to the 3 halves power times, now get this part, we're integrating uh, d theta k hat from 0 to 2 pi, so that's just going to give me 2 pi k hat, and that'll give me another r, so that'll be r squared as well. Make sure I didn't accidentally copy an R twice, though the R that I had before was in front of the d theta. All the other R's are additional, so that's the R squared over top of that. That looks good. And that's the actual result. Anybody have any questions on that? We can make it a little better if we'd like by cleaning up some stuff. For instance, the fact that we have a 2 pi and a 4 pi in it means we can cancel out some of that. So I'm going to do that real quick. And that gives us B is equal to mu 0 I r squared divided by, now the 2 pi canceled out with the 4 pi downstairs and just left the 2 downstairs. So now, there goes my stupid program turning into a eraser again. So I get 2 times r squared plus z squared to the 3 halves, and that's all in the k hat direction, and that's the result. Anyone have any questions on that? Now, something you might notice, and this is kind of interesting, if you perchance considered z equal to 0, so in other words, if you tried to calculate the magnetic field at the center of this loop of wire, but not above it or below it, but dead center right there, if you wanted to do that, you'd get the following. So for z equals 0, b becomes, notice you're going to have a r squared plus 0 squared to the 3 halves power. So that's going to make r cubed in the bottom and r squared on the top. So that's just going to give you a u0 over 2r like that. And that's in the k hat direction. So that's what it would be at the actual center. And more specifically, you might recall that this was due to a circle of angle 2 pi. In other words, if I didn't go the whole angle 2 pi, then the integral would have still came out the same, because sine theta and cosine theta, they could be a little different. But well, I won't say that. I'll just leave it at this. But this is going to come in handy in a second, because we're getting ready to do one more Biot-Savart law that's a little more challenging initially, but is going to be a real lifesaver. So keep that formula in mind that I just derived in the red, as well as the one that I put in the red box. Anybody have any questions on that before I move along? I see that a couple more people have signed in since we started, so I just want to remind everybody to chat me your first and last name if you haven't done so already. So we've just completed a another example using the law of Biot-Savart, and this is not unlike example 2811. So I'm just going to say like example 2811. Now I'm going to do an example that uses the Biot-Savart law, but it's a little bit odd. And in fact, this one's going to be, uh, yeah, this one's going to be example 2812. So example 2812 starts off with a coordinate system. And it's a little weird in that this one is, at least appears to be, an innately two-dimensional problem. The actual third dimension is coming into play, because that's going to have to be the direction. But in reality, what we're talking about is it's sort of two-dimensional, because all this stuff can be drawn in 2 dimensions. So what I'm going to do is I'm going to say that this is my y-axis and this is my x-axis, and that means by the right-hand rule, okay, right-hand rule means hold your fingers like this when we're talking about a coordinate system. Hold your fingers like this. This is your x-axis, this is your y-axis, and then your z-axis has to point in the direction of your thumb. So you see that when I hold my hand like this with the x pointing to the right like this one is, and my middle finger pointing up like the y is, then the z comes out of the page. So that's what we're seeing here. Now, here's the problem we're trying to solve, though, where we have a wire that comes down carrying a current, and then that wire makes a quarter circle. It's not going to look like it because I'm drawing it by hand, but it makes essentially a quarter circle and then turns off like this. So what we have is basically a current going downward, and then a current going this way, and then a current going this way. And what we'd like to do is calculate the magnetic field at that point P right there, where Z equals 0, in other words, at the origin. So that's what we're going to calculate. And we know B, or dB, is equal to mu 0 I over 4 pi, leave the integral off, dl cross rp minus rdl divided by rp minus rdl magnitude cubed. Okay, so I'm going to break this up into three parts. Part 1, part 2, and then part 3 is going to be that curved part. Okay, so let's start off with part 1. The big thing is, for each of these parts, I need to think about what DL is, what RP is, what RDL is, and so on and so forth. So let me explain them and give you what they are, and then see if you agree with me, rather than me trying to ask you to fill it out on your own. Whoa, I don't know what happened. Oh, there I am. Sorry. So first off, DL is supposed to be a differential line element pointing the same direction as the current, and that means DL in this case is going to be dy, negative dy, times j hat. Because all we know is it has to be infinitesimally long. It has to point the direction of the current, which is in the negative y direction, and it has to be a vector. Okay? So I made the length dy, I made it negative j hat direction, so that fits the criteria. So that's what the DL is. The RP is very interesting. The RP is a vector that points from the origin to the point P, and of course the origin is the point P, so in this case RP is just the zero vector. Now the RDL is a little meta here, but that's supposed to be a vector that points from the origin up to the end of the DL vector. So in this case, I need a vector that points from the origin up the y-axis. So that tells me that its length is going to be y, and its direction is going to be positive j hat. So I'm just going to say y j hat like that. But the criteria of this that we need to understand is that z can only, or y can only go up to, or must start at, let's say r, because we're imagining the radius of this is r. So I can only consider y being r or larger for that particular portion of the integral. Now, the whole reason I took the time to do all this is I want you to understand that we have dl is going to be crossed with rp minus dl, and rp minus dl minus RDL like this. That vector is literally 0 minus y j hat. So it equals negative y j hat. And when we take a cross product of DL with that, these two vectors are parallel. So that result is 0. Does everybody see how that's the case? Anybody have any questions about why that's 0? All right, so now I'm going to do segment 2, and I'll do that right here. For segment 2, DL is going to have to be, can one of you guys tell me what you think DL is going to be? Remember, the only rule for DL is it has to be infinitesimally long, So it's going to be really short, in other words, and it has to point in the direction that the current's traveling. And we're talking about the horizontal segment of the wire that I labeled 2 here. So can anybody tell me what the vector DL will look like here? Okay, so the DL has to point to the right, which is the positive I hat direction or the positive X direction. So we're just going to call that DX I hat. Oh, I just saw that Alex posted something. Sorry about that, Alex. So DL is DXI hat. Now let's see if anyone can tell me what RP is. RP is a vector that points from the origin to the point P at which we wish to know the magnetic field. Currently, we wish to know the magnetic field at the origin. So what is the vector from the origin to the origin? That's the zero vector. Okay. Now I got to do RDL, and this is the vector that points to DL. And we know it's along the x-axis, so why not use x as the length? And we also know that it's got a point from the origin to the DL, and the DL is going to be out here at x equals r or greater, in other words. So RDL in this case is just going to be x I hat. And of course, that means RP minus RDL is just going to be negative X I hat. So that means DL cross RP minus RDL has got to equal DX I hat cross negative X I hat, which gives us negative x dx I hat cross I hat. And this is what I didn't show you last time, but I hat cross I hat has to be 0, so that's why that one came out. So again, like I said in the previous line, it's because the two vectors are parallel. That's the same thing here. Parallel or anti-parallel doesn't matter if the difference in the two directions is 0 degrees or 180 degrees, the cross product will be 0. So now you see anytime you have a current headed towards the particular point that you're wishing to know the magnetic field at, then automatically that particular current cannot produce a magnetic field at that point. So that's something that'll help us in future problems. Now my job is to figure out part 3, and I'm going to go ahead and write part 3 in blue just because that's the one we're going to work with. Now, in this case, the direction of r of the dl vector is going to be sort of in our negative theta hat direction. So I'm going to say dl is going to be negative r d theta hat, which you guys remember is negative r d theta, and then theta hat is negative sine theta I hat plus cosine theta j hat. So when I distribute that r, or excuse me, that negative, I'm going to get r d theta times sine theta I hat. Oops, almost read it the wrong way. Sine theta I hat minus cosine theta j hat, like that. So now I have dl vector, and I need the rp vector, which we already know. Rp is 0, but I need the rdl vector. So the rdl vector is supposed to point from the origin to the differential line element, which could be basically this right here could be a representative model of RDL. So I'm going to say that vector is in fact R times R hat, basically. And that R hat is going to be cosine theta I hat plus sine theta j hat. So I'm writing it that way. So you can see the x component again is just r cosine theta. The y component is just r sine theta. That's the main thing we're seeing. So now we can go about computing this and we can say b is equal to the integral of db, which equals mu 0 I over 4 pi times the integral of, this is just for part 3 now, so I'm going to say uh, r, oops, switch to eraser again, r d theta times sine theta I hat minus cosine theta j hat. That's all going to be crossed with rp minus rdl. rp minus rdl is clearly equal to negative r cosine theta I hat minus r sine theta j hat. So this is going to be negative r cosine theta I hat minus r sine theta j hat. And then all of that will be over the magnitude of rp minus rdl, which you can see is just r, and it has to be to the third power, so that's r cubed. You can see right now that there's a common factor of r from this. There's a common factor of r from this, so this r and this r is going to give me r squared, and that r is going to cancel out with it and leave just a single r in the bottom. So now I can say mu 0 I r squared over 4 pi r cubed. That's me taking an extra step to show you what I just said verbally, which was the r squared is going to cancel out with the r cubed, leaving just a r in the bottom. And now all I have is an integral of, now I've got to do the cross product, and it's not going to be that bad, but I'll put the RD theta right here, and I'm first going to do the distributive property. So I have sine theta I hat is going to be crossed with negative r, or negative cosine theta j hat, and I've already taken care of these r's, so I don't know why I drew the r there again, other than I'm a goober and wasn't paying attention. So there's my d theta. So the first distributive property is sine theta I hat crossed with negative r cosine theta I hat, but that's going to give me 0. So I'm just going to put 0 there for that one. That's for this guy. Let's do it in a different color. I'm going to say that's for this guy and this guy. I got 0. And now I'm going to do it for this guy and this guy. Again, I've already taken care of the r's, but the main thing is, in this case, now I've got sine squared theta, and it's going to be a negative. So it's negative, oops, need to switch back to blue. Negative sine squared theta times I hat cross j hat. Like that. That takes care of those two. Now I'm going to do the second term in the first one, and this time it's cosine theta times that one. So in this case, I've got negative cosine theta times negative cosine theta, and that one gives us, of course, a positive cosine squared theta. So I'm going to say plus cosine squared theta. And then that's j hat cross I hat. Now, j hat cross I hat is in fact negative k hat, so that's going to make it a negative later, but we'll see that when we get there. So now I've taken care of this one, and now I've got to do the second term with the second term, but that's j hat cross j hat, so that one's going to be 0 again, so I'll just say plus 0. now I'm going to continue with my zeros, and what I get is mu 0 I over 4 pi r times, now in this case, I've got a negative k hat for both of them. And the reason, well, actually, let's see. I hat cross j hat, we can already work that out as k hat. There's some neat ways to figure this out, by the way. Specifically, if it's a cyclic permutation of 1, 2, 3, of 1, 2, then it'll always make 1, 2, 3, and all of them will be positive. So I is 1 because that's the first variable x. J is 2 because that's the second variable y. And k is 3 because that's the third variable z. So if you write 1, 2, 3, they're all positive. If you write 2, 3, 1, they're all positive. If you write 3, 1, 2, they're all positive. But if you do a non-cyclic permutation, then the answer you're going to get is going to be a negative. So like right now, I've got 1, 2, and the other answer has to be 3, but since it's 1, 2, it's in a cyclic permutation, so it's positive k hat, and 2, 1 here gives me negative k hat. Because that's 2, 1, all I can do is, because they all have to be different, is 2, 1, 3. But if it's 2, 1, 3, that's not a cyclic permutation, so it has to be a negative 3. So with that in mind, you see that we now have a negative sine squared theta k hat plus or minus cosine squared theta k hat. So I just pulled the negative out in front because each of them have a negative, and I'm pulling the k hat out in front because each of them have a k hat. And basically what we're getting is the integral of sine squared theta plus cosine squared theta d theta, but we know sine squared theta plus cosine squared theta is just 1. And in this case, I'm integrating it from theta equals 0 to just plain pi over 4. Excuse me, pi over, no, it's pi over 2. No, pi over 2 would be 90, so it's pi over 4. Yes. Okay. Now that's a key point, and I want you to see what this is. So basically, what we're getting is negative mu 0 I over 4 pi r. I'm leaving a space and then I'm writing k hat because what I want to put right here is delta theta. In other words, what angle did this thing go through? In this particular case, delta theta is pi over 4. Remember, pi is 180, and then pi over 2 is 90. Oops, it's supposed to be pi over 2. My fault. Glad I went to explaining that to you guys because I clearly had made a mistake in my head. So pi over 2 there, and this is going to be pi over 2 down here as well. And I don't think it's bad for me to use it in purple because I hope it stand out a little bit. But basically, the change in angle that I went through for that whole arc was that the arc was basically a pi over 2 angle. In other words, a 90-degree angle. So the answer for this is going to be really generic. No matter how many pieces of arc we have, it's always going to be mu 0 I over 4 pi r times the angle that the current has to go through the arced part of the wire. The wires that are that have the current headed to the origin or away from the origin are never going to contribute. And then all you have to do is multiply the mu 0 I over 4 pi r times the angle through which it goes, and then you multiply it by the k hat or the negative k hat, depending on the right hand rule. So in this case, the answer is just this. B is equal to negative. Now notice when I take the pi over 2 and multiply that by the 4 pi r in the bottom, the pi's are going to cancel out and I'm going to get an 8. So this is going to be negative mu 0 I over 8 r times k hat. That's the actual answer that we were shooting for. But the more important thing is the general result that I just told you about. So, for instance, notice the right-hand rule. If the right-hand rule, when you're talking about a current carrying wire, is you take your right hand and you point your thumb in the direction of the current. So, if you imagine this little piece of arc that's going down and to the right, then I have to point my thumb down and to the right, and I grab the wire this way. That shows that my fingers are curling down into the page. That means the direction is into the page, and we already found out from the right hand rule, since I drew x hat to the right and y hat up, the k hat is coming out of the page, so that's why we got the negative k hat. So that's why the direction is negative k hat, but that formula is always going to work. So for that to sink in for you guys, now that you've seen this, I want you to be able to apply this to any type problem. So let me show you one real quick to see what I'm talking about. So this is just an example that I made up, but there's a ton of them in your book and you should look at them. But let's say we had, for instance, a coordinate system that looked like this. There's my x-axis. There's my y-axis. Let's say I have a current coming in right here, and then that current is going to make a arc like this. So in this case, the arc is a full pi, and then it's going to come out this way, and then it's going to turn again and make a quarter circle, and then it's going to turn out again, and then it's going to make a quarter circle this way, like that. And what I'm going to say is the current is coming down. It's going this way. It's going this way. It's going this way, this way, this way, and this way. And what we have here is this one has a radius R1. This one has a radius R2. And this one has a radius R3. Now, by the right-hand rule, the magnetic field at the origin due to, I'm going to call this part 1, I'm going to call this part 2, I'm going to call this part 3, part 4, part 5, part 6, and I forgot one, so I'm going to call that part 0. So the magnetic field due to part 1 at the origin is, notice if I grab that with my right hand so that the current's pointing down, my fingers are actually diving into the page. So this one's in the negative k hat direction. For part 2, it is 0. Because remember, I told you anytime you had a current that's aimed towards or away from the actual point at which we wish to know the magnetic field, then that's not going to contribute at all because the DL and the RP minus RDL are going to be parallel. So when you take the cross product, it gives you 0. Now, since I hadn't done 0 yet and I already went to 2, I'm going to go ahead and do part 0. So for part 0, it is 0 as well. For part 3, if I grab that, I see that's in the negative k hat direction. It's in the negative k hat direction. For part 4, that's a 0 again. For part 5, that one's in the negative k hat direction again. And then for part 6, it's 0 again. Okay? Now, the only difference is in each of these cases, we have different radii, but we also have different angles. So the formula I just gave you was B is equal to plus or minus some unit vector mu 0 I over 4 pi r times delta theta, like that. And I'll say some hat vector. Hat. In this case, in most cases, I normally draw it such that the magnetic field would point in the plus or minus k hat direction. But in principle, they could put it in any coordinate system they wanted, in which case you'd have to come up with an I hat or a j hat or a k hat. So that's why I just wrote it that way. So for part 0 and 1, we got 0. So 0 and 1 and 2, or 0 and 2, excuse me, not 0 and 1. For 4, 0 and 2, and 4 and 6, we get no contributions. And I mean no contributions to the magnetic field. For part 1, we get B is equal to negative mu 0 I over 4 pi r. In this case, it happens to be r1. And in this case, the angle has to be an actual pi. And it is a k hat. So this one turns out to be negative mu 0 I over 4 r k hat. Now that was for part 1. Now I'm going to do for part 3. B in this case is going to be, again, negative mu 0 I over 4 pi. This time the radius is R2, so I'm going to put that there. And the direction is k hat, but in this case I've got pi over 2 and then k hat. So this is going to equal negative mu 0 I over 8r k hat. And then for part 5, B is going to equal, again, negative mu 0 I. This time it's over 4 pi R3. That was supposed to be an R2, and that was supposed to be an R1. I don't know why I dropped them, but I got it now. There's the R3, and this is also going to be an angle of pi over 2 and k hat. So in this case, I get negative mu 0 I over 8 R3 k hat. So B at the origin is equal to mu 0 I over, and I'll put a negative out in front just because they're all negative. So mu 0 I, and they all have a mu 0, they all have an I, and they all have at least 4 in the denominator. So I'm going to write that there. And then I'm going to say 1 over R1 plus 1 over 2R2 plus 1 over 2R3, and then all that times k hat, and that's the answer. So now you can see how, as long as you just completely do in pieces of arc and lines that are aimed towards the origin, you can come up with any kind of configuration you want and calculate the magnetic field as a result of that. Anybody have any questions on that one? All right. So now I've got to teach you about Ampere's law. And for that, I want to remind you a little bit about what we did with Gauss's law. So Ampere's law is the following. Ampere's law says the closed integral of B dot dl is equal to mu 0 times I enclosed. And if you remember, Gauss's law was the closed integral of, excuse me, E
This
dot,
class
notice,
ended 7.
yes, go ahead,
Did this class end at 7? Or,
650.
oh, because I had a couple questions about something else, but our lab
Okay.
starts at 7, so
Oh,
I'm
if
not
your
sure.
lab, yeah, if your lab starts at 7, you might run out. If you want to, feel free to send me a text during lab or after lab, and I'll try to answer it tonight. It won't be a problem,
Well,
Jasper.
I sent you a text on Sunday, hoping to get something back from you.
Oh, I'm sorry. I didn't send.
Before the assignment was due yesterday.
Which assignment was that? The practice test? I mean,
Uh,
the online
no, the
test?
homework that was due last night.
There wasn't. Okay, I can give you an extension on that. That's my screw up. I thought I actually intended to answer everybody's texts on that day, so I must have just missed yours. So just send me a text tonight, and I'll go ahead and correct your points because that's clearly my screw up. I'll correct your late assignment, and I can answer those questions. Can I just look at the text that you sent Sunday? Would that take care of it, or have you got
Well,
new
that was
questions
just
in addition?
asking if you had. Well, I was just asking if you had time to help
Okay,
me before the assignment was due. My
gotcha.
other question was about the the first extra credit assignment. I think there's a couple questions that the answers might be
Might be.
marked wrong when they should be right.
Okay. Yeah, that's cool. I'll look into that and if you want to just take a photo of it of the ones that you think might be erroneous or any questions you have, just send me a photo and I'll answer it as best I can tonight. Okay?
All right, we'll do. Thank you.
All right. Sorry about that, Jasper. That's my fault, bud. All right. So, what I was saying was Gauss's law was the closed integral of E dot dA equals Q enclosed over epsilon naught. So, notice there's something similar. They both have an enclosed quantity, Q enclosed for Gauss's law and I enclosed for Ampere's law. They both have a factor that has a subscript 0, and they're in reciprocal relationships, just like we learned when we did the magnet. Oh, actually, I haven't done that yet, so never mind. I won't tell you that part. But anyways, one has a mu 0, which is called the permeability of free space, meaning a vacuum, and it's 4 pi times 10 to the negative seventh. The other one has the permittivity of free space, which is epsilon 0, 8.85 times 10 to the negative 12th. But the other difference is they're both integrals with circles on them. The circles mean closed. So this specifically says, hey, these two laws are not laws unless you're talking about over closed something. So in the case of Gauss's law, it was a closed surface, and we called that a Gaussian surface. And the integral of E dot dA, where dA is a differential area element, is the left-hand side. On Ampere's law, the left-hand side is the integral over a closed path. So it's B dot DL instead of B dot DA. So that's the big problem here. So let me show you how we can deal with this. I'm going to start off with just a single current carrying wire that's infinitely long. We've already derived this using the law of Biot-Savart. I'm going to assume the current is in the upward direction. Now, what we know from the law of Biot-Savart is that when we have, let's say this is the z-axis, and let's say this is the x-axis and this is the y-axis, we know that when we have a vertical current that the magnetic field will go around it in a right-handed rule sort of way. So I'm going to go ahead and say that my hypothesis, notice this is part of another paradigm that I told you you need to know. So my hypothesis is to be made about the magnetic field. My suggestion is that the magnetic field is going to be some magnitude that only depends on the cylindrical variable. I'm going to call it rho this time. I normally call it lowercase r with a subscript CYL, but since y'all are doing that extra credit assignment and I did everything in terms of rho, I wanted to use that. So I'm saying the perpendicular distance, meaning perpendicular to the z-axis, from the nearest point on the wire to the point at which you wish to know the magnetic field, that coordinate is rho, and the magnetic field will point in the theta hat direction. If the current were going down, I would have said it had to be in the negative theta hat direction. But in this case, the right hand rule dictates that it's going to go around that way, which is clearly the theta hat direction. So that's my hypothesis. Now I write out the left hand side, but before I can do the left hand side, I've got to come up with a Amperian loop. So before I came up with a Gaussian surface, now I'm coming out with a Amperian loop. Now the Amperian loop has to be a closed path. So it could be, anything like this, as long as it starts and stops at the same spot. But in this case, because I want to be able to extract that magnetic field out of the integral, I need the magnetic field to be parallel to the differential line element on that path at every point. Or another way of looking at it is I need the magnetic field to be to be a constant on that path. If I have multiple parts, then it has to be a constant on some of them and zero on the other ones. Okay, zero meaning B dot dl is zero. So if the magnetic field is perpendicular to the path at some points, then that one won't contribute, and that's fine as well. So I want only parts of a path that have the magnetic field parallel to it, and therefore the magnetic field is a constant on it, or the magnetic field is perpendicular to the other parts, and therefore B dot dl is zero. In doing that, that means my Amperian loop is going to be a circle centered on the wire. So I'm going to say that is my Amperian loop. So that's my Amperian loop. And according to the right hand rule, if I integrate in a way that the right hand rule says is consistent with the thumb direction being the direction of the current, then I get a positive on the integral or a positive for the current. Otherwise, it's a negative. So I'm going to integrate around in this direction. And now I can say the left hand side of B dot dl is equal to the integral of b of rho theta hat dotted with, now my dl is supposed to be a little tangent vector along this path. That looks a lot like the dl vector I had just in the last problem. So I'm going to say the radius of this Amperian loop is r, or excuse me, yeah, I'll say it's r. I really want to say it's rho. I'm going to say it's rho. So I'm going to say it's rho d theta theta hat, because rho d theta is just like r d theta before. Now, on that Amperian loop, the rho is a constant, and so is b of rho, since b can only depend on rho. So I get rho times b of rho times the integral of d theta theta hat dot theta hat. Notice the d theta is, I'm using the linearity of the dot product so that I can pull all the scalars out in front and just let the operators of the dot product operate on the vectors. And of course, the magnitude of theta hat is 1. The magnitude of the other one's also 1. And the angle between them is 0. So we get, in fact, just 1 for that. And what we end up getting for this integral is the integral from theta equals 0 to 2 pi. So this is going to be 2 pi rho times b of rho. Now, just like Gauss's law always gave us an electric field times an area, Ampere's law is always going to give us on the left-hand side a magnetic field magnitude times a length. and it might have some other terms. It might have multiple terms that, B times L plus B times L, but it also have other terms that is plus zero or plus zero or plus zero, so on and so forth, just like we did with Gauss's law as well. So that's how the left-hand side came out. The right-hand side is supposed to be the current enclosed. And really, what that means is any surface for which that Amperian loop could be an edge, then any current that pierces that surface would be considered I enclosed. In this case, since the I enclosed is up and we're integrating around, that's consistent with the right hand rule. So mu zero I enclosed is just mu zero times positive I because it's consistent with it. So now I say left hand side equals right hand side, just like we did with Gauss's law. And this gives us 2 pi rho b of rho is equal to mu zero I. And lo and behold, we get B, according to our hypothesis, is mu zero I over 2 pi rho theta hat, which is exactly the formula that we found by using the law of Biot-Savart. So that's not enough to finish this chapter. I'm going to make a couple more videos of this, but I really think I need to spend the time with you. So, in our next meeting, which will be Thursday, I'm going to finish off these Ampere's laws applications and introduce a magnetic dipole moment and that sort of stuff. But you guys are free to go. Make sure you chat me your first and last name if you hadn't done so already. Jasper had a couple of questions. He's going to text me on that or something along those lines, so I'll try to answer him. But I'm here until the last person leaves in case anybody has any questions. Thanks for coming, everyone.
I was gonna. What is your office hours tomorrow evening? I think I might just try and join you then.
Okay, tomorrow evening is the same thing. Basically, if you show up at like 6:40, 6:45, I start up at 6:50.
Okay, yeah, I'll probably do that. That'll be easier than trying to ask you through text and get pictures and stuff.
No problem. I'm real sorry about that, Jasper. I can't believe I missed your text. I'm usually pretty good at that, but I apologize.
Okay, thank you.
All right, have a good one, sir. How about you, Giovanni? You have any questions, sir?
Yeah, just one for the when you were doing that problem, the one that had a whole bunch of arcs,
Mhm.
how did you orient your hand to know that it was going in the negative K head?
So let me use something. Okay, I'm trying to figure out something I can use as a diagram. So if you imagine this is the arc of the current, and the current was going down this way, then my right thumb has to point the direction of the current, and my fingers stick through. So when the current was going down and to the right like this, my fingers poke through. That means that the magnetic field points into the page. And because the X is to the right and the Y is up, a right-handed coordinate system would have the K hat pointing out of the page. So I had to say negative K hat because it points in the opposite direction. Does that
Okay.
make some sense?
Um,
It's a lot of
kind of,
words.
but yeah, I mean, if you'll just upload this, I'll just rewatch it and then, repeat it
Yeah.
until I get it.
Also, remember, like if this is a wire, see how the this points up? That's the
Yeah.
direction of the current. So if it's just a straight wire, you just take your right thumb and point it in the direction of the current, and then your fingers curl around this way. So your fingers curling around that way says, oh, the magnetic field is going to be a constant on a circle and it's going to point in this direction. So there or there or there or this way when it's at this point. So that's another way of looking at it. And you can just do each little part like on an arc. This was for a straight line, but on an arc you have, a itty bitty bit that's straight right there, and that would make the magnetic field pointing that way. And then you come over here, it's bent this way. That's to make the magnetic field go that way. Hopefully that'll help you. Between that and some of the other videos you might see, I did have one of my students tell me that the videos that Pearson offers are pretty helpful. You might look into Ampere's law and Biot-Savart law in that. They might have some decent videos there too. But of course, mine are here as well.
Okay, yeah, because I know with like in chapter 27 when they show you like the three different right hand rules. The way I've been doing is like just orienting it so like the magnetic field comes out of my palm, I think.
Okay, gotcha.
I
Yes,
think.
you're sort of doing it like this, and you're sort of picturing this as one of the vectors, this is a vector, and this is a vector. That's another type of right-hand rule you can do.
Yeah. All right. Well, that was all.
Well, feel free to ask me any more questions, or if you think you've got it figured out and you wanted, wanted to explain it to me and see if I agree with you, you can do that. You can send me a video or whatever. I'll be
Okay.
glad to help you. All right.
All right. Yeah, and also with the extra the face-to-face extra credit things, the three
Uh-huh.
assignments.
Yes.
Like Dylan was saying, I think it was for the infinite plane one.
Uh-huh.
I think it was because I think it was asking you for the constants and like the formula for it. And I think the answer it took was rho as the constant, even though I think it was sigma.
Okay. Yeah, I
Or I
will
don't know
check
if
that.
it's because
That
you
sounds like
use
an easy
the
typo that I might have made.
or I don't because I thought it was at first I put sigma, but then I thought rho because I thought 'cause since you use like the soup can shape, I don't
Hmm.
know if that would change it. But I don't know, but it took the
It
at
sounds
least I
like
think
you're
it took
figuring it
the
out, though. This is great. I mean, the questions you're asking are exactly the kind of questions and exactly the kind of thought processes that you have to do. So that's good. Yeah, I'll check that out. And if you find one, let me know. Remember, I'm giving you extra credit points for finding any errors I have. So that includes, for instance, Jasper. If he found an error, then I'm going to give him an extra credit point on it. And same thing with you, even if y'all both find the same one. So just, tell me whatever you found, and if it turns out to be an error, I'm going to give you extra credit points for it.
okay.
Okay.
Hmm.
Thanks. Have a good one, Giovanni.
All right, you as well. Take care.
Thank you.